Meow. Hello, everybody. Welcome to the first ever Safe Spring Saturday Seminar Series. I'm Lana, and this is Callie, and we're from Team 12827, the Crazy Cat Ladies.
We are happy to introduce the winning Alliance captain at the Florida State Championship, Team 6433 Neutrinos. So without further ado, take it away, Neutrinos.
Hello. So my name is Akshat,
I'm Nishan. I'm Shrikar.
and we are from 6433 The Neutrinos.
So first, we want to talk
It's important to learn from your mistakes and
reliability, and that's a really important thing. And how to build a chassis, and then finally we learn how to program it, which Shrikar will talk about. So since this was the first year that we used mechanism wheels, we also had to create a new teleop and autonomous base code for it. So for teleop, we use sine and cosine so that the left joystick could control movement while the right joystick could just control turns. And this was kind of simulating like modern warfare shooting games like Halo or Call of Duty, which we like played a lot. So we just thought we could move it to the robot and make it easier for the drivers. Another thing we did was PID for autonomous, and that's the first time we used PID and encoders rather than time based. And then we started this during the summer so that we would have enough time to transition into the season and then work out any bugs before it started. PID is proportional integral derivative, so rather than just using the same power to go to the same place, it'll decrease your power in proportion to the error. So when your error decreases, meaning that you're closer to your target position, your power will also decrease and it'll make fine adjustments along the way so that it keeps it in track. And then next season, we're considering doing odometry maybe during this summer so that we also have it ready during next summer. And then that'll kind of propel our game forward.
So over the summer, another thing we did was we bought the 3D printer. That kind of helped us customize and mobilize a lot of our pieces. That we did get to use a water jet and laser cut some pieces, and such as these linear blocks that we use for this season. Over the summer, we did assemble an entire linear slide design and all of the pieces for it by 3D printing it. We started off with a 3D printed model. We transitioned it to a aluminum cut, water jet cut piece. And all of that was possible through the luxury of having a 3D printer and creating those prototype pieces, right? Obviously, it did help us in season to create all of these designs and having that ready to go. With the height restrictions, we're easily able to get those pieces cut and reassembled for the upcoming robots for the in season.
So in the past, for the linear slides that we had to like make these crude kind of blocks to attach the linear slides together. But now that we had a 3D printer this season, we were able to make fine designs in CAD with the exact dimensions, so that we could make the connections between the slides much more streamlined. Having the linear slide design already together before the season made it a lot easier to implement during the season when we needed to get it done. So now we're going to transition into what we did during the season.
All right, so during the actual season, we started off by creating several prototypes right when the game started. We had a grabber prototype, we had a wheel intake prototype, and we had prototypes for different types of outtakes, right? To start off with the grabber prototype, the thing that we used at the very end, we started off with a very simple design. The design wasn't the most structurally stable, but it did work as a prototype. It had several iterations that allowed us to take it from tournament one to tournament two to tournament three and make it better and more structurally stable so that within a hostile game environment, it would survive. In regards to the wheel intake system, when the blocks were intake, the problem would be how the outtake process would work, right? And having a two system intake outtake process, we felt like just wasn't appropriate for us. And so we decided to stick with the simplicity of the game and stick with the grabbing mechanism. We understood that with the grabbing mechanism, although intake might be a little bit worse than the wheel intake, we understood that having driver practice was extremely crucial, right? With driver practice, we were able to create test runs, have a break-in period for the actual robot 2 weeks before the tournament. That break-in period was really, really important because in the previous years, we haven't done that. And because of that break-in period not being there, it cost this game like Suha said, right? On one of our tournaments, a wire disconnected, and that was a maintenance issue, right? And if we had broken in the robot, maybe we would have won that game and went on from states to worlds, right? And so this where we made sure to prioritize on that. The drivers were able to intake the block seamlessly and then outtake them very seamlessly as well.
so to increase the reliability in our robot, we tested all our parts rigorously. So first, as Akshat said, we had all those prototypes. And when we developed them into finalized pieces that were supposed to go onto the robot, we tested them extensively as individual parts so we would find any flaws before we actually began building the robot. And then after that, once we put the robot together, we tested them all together to find any flaws that we couldn't have seen when they were tested individually. So the whole robot as a whole was reliable and worked as we had intended. So we also believe that it's important to experiment with many types of parts and even the unconventional ones to find the most optimal design and the one that'll take you the furthest.
Yeah, for example, like when Suas, he just mentioned the unconventional parts that we used. We used glove material to improve the grip on our grabber, and we used a hose for wire management on our lift. So we found it important that we experimented with all these different parts because we never would have come across such unconventional solutions to the problems that we needed to solve.
Another thing that I would like to talk about is our inspiration from other teams, really. So we attribute a lot of our design to actually things that we've seen on maybe YouTube videos or Reddit, and that's actually where we got our idea for like the first robot. And then we kind of took our own inspiration to make it different and then make it unique, which is I think what led us to winning state championship. And another thing that I want to emphasize is our priority on failing. And then this might sound silly, but we tried to fail as much as we can in that 2 week period that Akshat mentioned. And then by doing this, we could basically solve so many issues during the tournament because we knew we've encountered it previously in one of our practices. And then once we've encountered that and figured out how to solve it, we could solve it in like 5 seconds again. So I think that's what helped us a lot. Another thing is that every time we started working on something, we had an image of how it would look in our head. So we began with our end in mind, and then we had that goal set in place so that we knew exactly the path that we needed to take to reach that. And we didn't have to just experiment and then do like crazy things along the way to get it. We knew exactly what we needed to do. And then finally, I just want to talk about programming. And that was a long experience, really, because it started at the very beginning of summer, and we were still tweaking it at the end of the season. So we used PID, which was completely new, and then this used 3 sensor inputs rather than one. So we used the encoders and tried to maintain the encoders be the same. It used the angle from the IMU, and it used 2 sensors. So these were 2 distance sensors that we put halfway through the season, and then those sense the distance from the walls. So using these 3 inputs, it made sure that we can map out any single part of the field and get it there in the most efficient uh, and maximum or minimum amount of time. We also didn't go for a 3 or 4 block autonomous because we knew that we could get a 2 block with a 95% consistency and then didn't want to drop to a 3 with 70% consistency. And then we didn't have any side grabbers. So our strafing was a bit slower than usual. And we switched to 312 RPM motors, but this still wasn't fast enough to do a 3 without losing consistency. So we dropped that idea entirely. And the last thing is that we didn't touch upon this, but we had practices every Saturday going from around 8 to like 3 or 4 o'clock, and we had lunch here as well. And then doing this keeps the entire team engaged, really. And then we had like fun activities in like between, since 8 hours is a lot of time. But we also had a ton of weekly calls and then text messages going through the entire week whenever we saw something or thought of something in the shower, like at bed. And the first thing we'd do is just text it, see what others thought of it. And we were really open to new ideas and then tweaking our own ideas to make things happen.
Going off what he said earlier about having a goal in mind and making sure that we implement and get all the ideas because we have all these ideas constantly to make sure they're organized and make sure that we have it all together. We wanted to or put that all in our engineering notebook. That was one of our weaknesses in previous years. Like we didn't keep up with it. It wasn't very comprehensive. It didn't have all of the details of our meetings and the changes that we made to the robot. So I wanted to improve that this year. So in the summer before the season started, I looked at other teams' engineering notebooks that were successful, and I wanted to like emulate the strategy they use, how they cover different information. So during the season, I started keeping like detailed records of each practice. These ideas were brought in. This progress was made. We need to do this next time, and that helped us keep everything together, be efficient at practices, and take advantage of our time.
So I think a lot of people would be wondering how did we come about our robot and how do we transition into the robot, right? To our final robot, right? And that's what I kind of want to touch upon. We started off with a prototype robot, right? That prototype robot was out of 18 inches. It did have this grabber-like design. It had some type of hinge idea for the entire robot for the entire grabber system to hinge back and then release and whatnot, right? But having that prototype robot there, we were able to, I guess, visualize how the entire functionality of the robot was going to work, and that's kind of what we stuck with throughout the entire season. In terms of functionality, the grabbing system stayed the same, and it was still out of 18 inches at that point, right? And now we wanted to make it game legal, right? So we took that design after we put together a bunch of prototypes, and we created CAD models. By creating the CAD models, we were able to ensure that the design would be within 18 inches, be game legal, and still meet that height requirement that was created by the game scenario, right? And then after doing so, we had a robot ready for the first, I think, four tournaments. And then having a ready robot for the first four tournaments led us to have numerous high scores, but it also allowed us to look at the different weak points of our robot, right? And so, knowing that the game was a little bit orientated to robot contact, we needed to make sure that our robot was also very sturdy. At that point, the robot did have a grabber that could bend because of its aluminum thin like piece. And so we decided to redesign the entire grabbing system, redesign the actual side plates so that they could take robot hits and whatnot, right? And this is what we had ready for this actual state tournament. The reason it took us so long to transition from the season, the league's tournament to the actual state tournament, having two different robots, was because we wanted to make sure that both the robots had their strengths, and it was an actual improvement rather than taking a step back, right? Like Shrikar said, we love to learn from failures. One of the tournaments where we learned from a failure was it was a league tournament, and it didn't cost us much, but it let us learn a lot from that tournament. We did make a last minute change, and because of that last minute change, it didn't cost us the game, but we did take a step back from the previous tournament. And after hitting that point of realization, we decided to make amends and ensure that there is a 2 week break period. We aren't making significant changes at the end, and we stick with a simplified design that kind of works throughout the entire season.
So I just want to kind of end it off with some of the key takeaways that we had. So firstly, is organization and keeping all of our ideas together. Next is consistency. That's what won us our tournaments, and that's what made us state champions. Every round, we were getting at least 80 points, 90 points. We weren't looking to get the world record every tournament and prioritizing that. We were making sure that we were getting consistent point totals because that's what leads to victories in the end. And finally, we wanted to, and that consistency not only translated in the building process, but also in our whole design process. Because, like as you said, the 2 week break period, we think that's like really important. The 2 weeks before the tournament, we make no changes to the robot at all. I think that's one of the most important things that contribute to our success because we didn't discover any issues at the tournament. We fleshed out all the issues beforehand. So once we got to the tournament, we were ready to go. Is there anything else you guys want to add?
I think we're good. So, do you guys have questions for us?
Yeah, actually, if anyone in the YouTube live stream would like to ask questions in the chat.
I actually have some questions right now. How do you guys practice driving?
So we practice driving by okay. So after we've completed the robot, and we have a robot that's all programmed and we're ready to drive. Then we have a driver one and driver two both drive around, figure out what's comfortable. As we feel like something's uncomfortable, we could change something here and there. Our programmer will take care of it. All of our team members have different ideas for how we can optimize the driving. I think Shrikar kind of talked about the modern warfare setup that kind of really helped us drive in a flawless way, right? And then other things in terms of driving is we like to set up obstacles in our path, or get another robot running maybe to get in our way to practice that driving and make it seamless.
And then also autonomous, we do it throughout like the weeks, but then we have that 2 week period. So in the first week, we only do driver practice, but then in the second week, we run an autonomous and then drivers, and then autonomous and then drivers. So we simulate real games.
We also set up different like situations. So sometimes we would assume our partner was disabled and we just set up an obstacle that we would have to drive around. Or we'd assume that they were a feeder bot and that they would place blocks near the line and we would practice that situation. Or we would go to the depot and they would also cycle and we would go in a circle. So that way we were prepared for any situation that we encountered in the tournament.
I also have another question, and if any of the teams who are watching on our YouTube live stream would like to ask the neutrinos any questions, please ask it in the chat. So how do you have an effective off season?
Off season, as in like the preseason beforehand.
Yes.
Okay.
Yeah, so it's really with the goal. So at the beginning of the off season, we knew we wanted to have a working mechanism wheel chassis. Since in the years past, we realized that a lot of games revolved around side to side movement as well as forward and backwards. And then we always had a normal tank drive or four wheel drive that we could use as a contingency plan if the game required climbing up slopes or things like that. So we knew we wanted to have a mechanism wheel chassis with the program working, and then that's just what we set out to do. So it wasn't really organized or structured during the summer. We just took the robot whenever we wanted. Like, for example, the robot was in my house for like a month or somewhere around that, where after the mechanism wheel chassis was just built, I would just program and then play around with the PID, making sure it was effective for the season. And the important thing to remember is that robots change. Like, it could work one night and then not work the next day. And then it's going to be totally possible that it's working throughout the summer, but not during the season. So it's always important to really understand all parts of your code and all parts of your robot so you know how to make your changes.
So in the preseason, you want to look at your previous season and identify where you felt weak, right? And then over the summer, you look at those areas and you try to figure out a way to fix that. So this season, we had a little bit of trouble with our chassis. So what we're going to be doing is troubleshooting that and fixing those problems.
So basically, to have the effective preseason, just to sum up what they said, first you need to put in a lot of time, because in the preseason you'll have a lot more time than you will during the season, because that's when school starts and whatnot. So you want to put in the time and make sure all of the main areas with their components are fleshed out. And also, when you start, make sure you have a clear goal in mind for the task. We wanted to get a mechanism chassis coded and working, autonomous PID figured out, and linear slides, and having functional linear slides. So if you set out a few important goals at the beginning, and make that really helps in the end to make sure you have it all done by the end of the preseason.
So I think while the goals are very important, I think experimentation is also equally important, because while experimenting, we can find new things, discover new things. Like Shrika kind of discussed, if we see new ideas on the internet, we're always willing and open-minded to experiment. For example, the 3D printer we bought, we immediately started experimenting with that, and that kind of helped us out a lot in regards to the prototyping process.
Do you have a large or small team / how do you have your team members work together due to the size of your team?
So,
We split into groups, and we don't only go where our specialties lead us. I love to program, but we also try to switch around and then make sure that each person knows every single part of the robot. So when it comes around in the tournament, we're able to fix it. And we always have a generalized understanding, since if you read the book Range, it talks about how a generalized understanding of the world is beneficial than a specific area in one part, and it enables you to see problems and solutions in a different way than other people haven't. So we try to do that. And we also, we're the most senior people on the group. So we kind of have a leadership role to play in it. We make the goals, talk through the ideas, figure out how we're going to make them compatible with each other, and then work them through each other. But we're so open to input. Like, we take every single idea seriously that comes from the team. And then each of us kind of leads teams of like mini teams of like 3 to 4 people. And then we just kind of switch out and then make sure that everyone has a task to do every single day, as well as making sure that everyone has their goal and then what they're going to accomplish.
Now, to make sure that the team as Neutrinos has its dynasty and it'll continue for years, we also make sure that the younger team members are being taught different ways to think, and they're also being taught the different designs and how to build a robot or how to program a robot. And that's something we prioritize, because once they get that throughout the years, they'll be better at what they do, and increase the team's efficiency by a whole lot.
Yeah, so we emphasize learning on the team, and we have, even though we have a lot of people, we try to take advantage of it with the different groups that we make sure everyone is always doing something.
To be specific, the first 15 minutes of practice, we literally have not a whiteboard, but like an easel kind of just paper. and then we'll just write down the tasks, and then whoever wants to work on a task will just raise their names or raise their hand, sorry. And then they'll just put their name right next to the task, and then we'll split up into groups of like 3 or 4 so that each person has like people to rely off of and work together to complete these tasks. And that way everyone has something to do every single practice.
All right. So one of the questions we got from the chat is, how many people are on your team?
Let's say around 11. 11 people are on the team.
Okay. I also have another question. How long do you test your prototypes before you know that they're ready to be built and be put onto the robot?
Okay, so we actually have a robot ready for just prototyping, and that robot will take any prototype that we think would be suitable for the actual game. And so what we do is it might take a week, it might take 2 weeks, right? There's no specific time period that that we'll know that a prototype will work. But usually, I would say it would take us like less than a week to actually build the prototype. Once there's an idea, after we actually build the prototype, it'll go on top on a prototype robot that has 4 wheels. We'll test the servos and the actual individual pieces of the prototype before actually putting it on the prototype robot. And once those individual pieces seem suitable, and I'll give you an example, right? We had the grabber, right? We wanted to make sure that the grabber had a firm grip on the actual block and it grabbed the block in a mold that we wanted to. And so what we did is we hooked up the servo to a battery and had it rotate, right? And by testing that rotation and how much how firm that grip was, we were able to conclude whether that prototype was suitable or not, right? And once we were able to make that conclusion, we transitioned into the actual robot, the prototype robot, and we tested with our drivers driving it around, seeing if it's if it works, how good is it in terms of intake, how firm is the grip, how firm is it in regards to the actual movement of the robot. And once we seem it's suitable there, then we transition to the final robot and we put it on there. And then obviously there would be iterations to that prototype, and that's what we do with the final robot.
And we're not really scared of failing. Over half of our prototypes fail, but that's just how it is. We go with the best ones, and then we just don't try to put everything on the robot. We take things off because sometimes less is better.
Yeah, we only put a prototype. We test it as long as we can to figure out all the errors. So only when we feel comfortable that we've fixed everything, that's when we put it on the robot. There's really no set time period. It just depends on the prototype itself.
And the complexity.
Another question from the chat was, how many robots do you have? Something else I wanted to ask is, do you have multiple robots to prioritize different tasks?
Right. So we kind of like I said, we have 2 robots, but both of those robots were for the actual tournament. We had one robot that was just a prototype robot. It was outside of 18 inches. That robot we built right when the season started. I wouldn't consider that as like a complete robot because it wasn't game legal. But I would say we built 2 robots and one prototype robot.
And we always keep one robot completely untouched. So if the robot we're currently building fails, we can always go back to the one we had before.
And we also have a chassis for programming, but that one we don't really prototype on.
Yeah, on just the 4 wheels so that we can figure out like how to move the robot.
All right. So I have another question. How do you prioritize your time throughout the season?
So what we try to do is we make sure that we have enough time to do everything. So at the beginning of the season, as we said, we start prototyping, and then we move into completing the robot. But we have to always be mindful that we leave enough time to complete programming and make sure that it's reliable, as that's also a very important part of the game.
And we also set deadlines. So for example, we have our 3rd robot, and then at the end of it was before league championship. It was 3 weeks before. and then we hadn't completed the lift, and then we said that if we don't complete the lift, we're not going to use this robot for the next tournament simply because we didn't have enough time to test it. So we didn't complete the lift, and then we stopped on that robot and then continued it for later. And it's really important since we have such a big team that you have a lot of tasks to do. So we were building two robots simultaneously, one finished faster than the other, and then the other one we took more time on, and then improved on designs that we saw at matches, saw online, and other things. And then we made sure that that one was consistent. So at the state championship and maybe worlds when we used it, it was going to work.
Yeah, so we, like you said, we set the timeline with the bare tasks that we need done. We need to have this done by this time, so we have enough time to program, enough time to test. Like if we, let's say, like last season, we would be like, if there was another feature that we wanted to add for the competition, we would add it. But now this year we made concrete deadlines. So if it was done, it was done, and if it wasn't, it wasn't. So we made sure that that what we needed was done, and we did extra only if we had time.
Okay. Can you give us any tips on wire management?
Oh, that's fun. Zip ties, use a lot of them.
Yeah.
They help. And then you need to have your wire management plan along with your chassis plan. So a lot of teams neglect that. And then we always neglected that before. We would build a chassis, build all the components, and then wire it last minute. But this year we decided to have these wires because we had so many wire disconnection issues last year and we didn't want to face that again. Just one wire disconnecting would cost us the whole match, especially it was like a servo on the grabber or something related to the expansion hub. So instead, what we did was decided where every single wire would go, along with when we built a chassis or catted the chassis, and then knew that these wires would go this way, and then this wire would go this way and connect to the phone in this manner.
Yeah, we were extremely conscientious when it came to like wire placement. So every couple inches we would zip tie it. And like we prioritize wire management designs, which is something we hadn't done in the past. First, we try to figure out like this snakeskin, which is something like you put the wires through, and then we like try to rubber band it in a certain way, and that didn't work. And that's how we came up with the hose as a coil to put the wires down, which was on our robot at the state tournament. So we wanted to like prioritize the wiring as much as possible this year, and be very careful how we wire it and where we wire it. And also like very key wires, right? Like the one going into the phone, the one going into the expansion hub. We made sure we had like special we had 3D printed attachments to hold in the wires that go into the expansion hub. And for the phone wire, we made sure that it was out of the way and that it would not be jostled by anything, so that it wouldn't come out during the match.
And also we ensured that every single wire was accessible during the tournament. Since if one wire failed, we could easily pull it out, replace it. So if we had snakeskin, then we would have to pull all the wires out, use a new snakeskin, and then figure out which wire was bad. Instead of that, we could just, with the coil mechanism, we just cut a zip tie, took the wire out, put a new wire, and zip tied it back.
All right, so we have another question. Do you have any unique methods for autonomous, and what do you use to scan field elements in autonomous?
Yeah, so initially we tried camera to scan the field elements, but this caused us so many disconnection issues, or not so many, but once every 8 to 10 matches, the robot would just not start and then disconnect, and that was because of the camera we were using. And then since the first tournament was coming up relatively fast, we decided to just use the color sensors we had in hand. Initially, we tried to just go forward, sense, go right, sense. But this would create exponentially more time depending on what block or what place the Skystone was in. So one day I was just in the shower and then I was thinking, like, what if we just went in once and then scanned 2 blocks, and then just by one scan you can know which one the Skystone is. And this worked fabulously. And then immediately I texted to the group. They liked the idea. It went through a lot of people, and they said we think it would work. So we decided to prototype it. We put 2 sensors, 2 color sensors, and then we just went up, scanned it, and then picked a block based on that. That was extremely fast and didn't cause any disconnection issues. And then that's what we did, since we only had to scan once and we knew which 2 blocks were the Skystones and could easily grab them. For autonomous, we have a couple of basic methods that are implemented in all of our classes. So we have a PID controller, and as I talked about earlier, this uses 3 error inputs. So this uses the encoders, which are just how many clicks the wheels have turned, and we just go build a 312 RPM motors. And then this is for the chassis, by the way. So along with this encoder, we also have the IMU. So we have 2 IMUs on our robot, and then we average out the values so that it's more accurate. And then based on that, we try to ensure that the robot is going straight while it's moving forward or it's strafing. or maybe it's turning. We haven't really implemented that many turns this game, but we had a turn mechanism in place so that it would turn consistently and in the most efficient amount of time. And lastly, it used two distance sensors on either side of the robot that would sense the distance from the walls. So based on this, we would know how far apart from the wall we needed to be at that second or third skystone, and how far apart from the right wall we needed to be to place the block on the foundation. So this really helped us, since we could just say drive right and then give three parameters: the encoder count, or two parameters: the encoder count, the power, three encoder count, power, and the distance from the wall, and the robot would just go there.
And also about the color sensor tree I was talking about, we it was very simple and easy to implement, but it did have problems going throughout the season. For example, like it was hard. It needed to be close to the block in order to sense it, so we had to figure out a way to have it in the front of the robot without being in danger of being damaged. And also, light conditions affect color sensing a lot, so we had to figure out a way to normalize for that, which Rico will talk about.
Yeah, so we actually used the blue value times the red value divided by the green squared. So what this enabled us to do is kind of made it proportional rather than an absolute value such as the red. So when there was more light, then the red value would increase and pass our threshold. But instead of this, when we multiply the red by the green and then divide it by the blue squared, then that means that all three values were moving up when there was more light, but the value would remain the same. So we decided that also that instead of implementing a threshold, we would do a comparison test between the two color sensors on the right and left. So with these normalized values, we would compare them. And if they were within one within each other, that meant that both of them were the same, meaning that both of them were yellow. But if one was a lot less than the other, or one was a lot greater than the other, then we knew which one was a sky stone and which one was a stone. So this comparison and normalizing helped it become a lot more accurate, but it still wasn't really as accurate as we wanted to be. I would say it's around 90%, but we wanted to get close to like 95 or 98. So we were trying to experiment with new color sensors. We found one that worked, but then Worlds got canceled, so we couldn't implement it at the next tournament.
Is there a specific way you guys manage your time during your meetings?
Yes, there is. So in the beginning, first like 15 minutes, we like to plan everything out. We figure out what everyone's doing. If there's different ideas, we'll note that down. That same plan will also go in the engineering notebook for us to look at later. Once we create that plan, we don't always follow the plan because there are ideas that come in throughout the practice, right? But we'll have a generalized idea of what we're going to do at that practice and continue with that. And once we follow that plan and we have groups of people doing things at the actual practice field, everybody will try to get everything accomplished throughout a certain time period, right? And that time period will usually end by lunch break. And by lunch break, we all recollect as groups and we talk about the different things we accomplished. Everybody pitches in their ideas and how we can improve on something, and where we feel like something is a little bit weaker, and where we feel like we could take something else and kind of combine two ideas and put it together or something, right? After we recollect those ideas, we again disperse back into groups, try to complete our given tasks. And if there's a new idea, we'll try to implement that as well. And by the end of practice, we're usually playing basketball outside, and having fun as a team, and ensuring that we have a sense of collaboration, teamwork, and having a fun aspect to being together.
Yeah, so basically the main three things that we need to manage our time is first the plan at the beginning of the day, plan during lunch, and finally at the end of the day, like right before we play basketball and like have the fun motivator, like and like the yeah the fun motivator for the practice. We come together and say what we've done. So next practice, we're not figuring out like where we were wasting time trying to figure out what needs to be done. We'll have it all written down so we can continue right where we left off.
And another important point to what Nishant kind of pointed out about wasting time in the beginning of the practice of figuring out what we're doing. Another way we ensure that isn't happening is by having phone calls every Wednesday or Friday. And with those phone calls, we pitch ideas, we figure out what different people are doing. And sometimes if people can't attend, we always have them up to date by the next practice.
All right, so a couple more questions. How long, yeah, how long do you test your prototypes before you know they're ready to build? And where did you guys make your shirts?
So, in regards to the prototypes question, how long we take to build our prototypes? Okay, so What we do is we take around a week or around 2 weeks. There's no like set period, kind of like what I said, to complete a prototype. But once we have a prototype in mind, we either decide to CAD it or build it straight on the spot. After creating a CAD or on the spot model, we implement it on the actual robot.
Yeah, and for our shirts, we made this design a few years ago and we printed them from custom ink.
All right, that's all the time we have for today. Thank you so much, Neutrinos, for sharing your wisdom with us.
Thank you.
Thank you so much for hosting us.
And next Saturday, make sure to tune in to the first virtual showcase, and SSSSS, whatever, will return May 9th at 12 p.m. Thank you for joining us, and we'll see you next time.
Bye.